Welcome to today's Deep Dive. I'm your host, and our mission today is to, well, explore how modern web applications can actually survive the dreaded offline dinosaur.
Oh, yeah. That little pixelated guy. We all know him. And I'm thrilled to be here to talk about how we're finally defeating him.
Right, because imagine you are reading this critical email on the subway. You've just finished typing out a really long, highly detailed response.
Yeah, absolute worst timing.
Exactly. The train plunges into a dark tunnel, you hit send, and instantly your entire screen is replaced by that bleak offline desert. Your email is just gone, the application is dead.
It is honestly one of the most uniquely infuriating experiences of modern life.
It really is. And, your first thought is probably to blame the developers for writing terrible code. But what if the code powering that website was actually perfectly engineered? What if the fundamental architecture of the web browser itself was the real problem?
And that, right there, is the core paradox of web development. I mean, for decades, we engineered these incredibly sophisticated state-of-the-art applications. But we just sort of accepted their profound fragility as a fundamental law of the internet.
Like it was just unavoidable.
Right. The exact second a single cloud blocked the sun or you went into a tunnel, the entire digital building just blinked out of existence.
So today we're diving into how developers are outsmarting that default browser behavior. We're relying on a fantastic narrative piece today titled The Secret Life of JavaScript the Proxy by software engineer and tech writer Aaron Rose. It's published on tech-reader.blog.
It's such a great piece. What makes it so compelling is how Rose frames this highly technical architectural evolution as a gripping story.
Yeah, he introduces us to these two specific protagonists, Margaret, who is a senior software engineer, and Timothy, her junior colleague.
Which is a brilliant stylistic choice, honestly. It grounds all this abstract code in real human frustration and problem solving.
And the setting is so vivid, too. They aren't in some, neon-lit, chaotic Silicon Valley startup with ping pong tables everywhere.
No, not at all.
They're working in this grand Victorian library in London. The author explicitly notes it's the kind of place where code quality is the unspoken objective. Craftsmanship is paramount.
They aren't just trying to ship a feature quickly to appease investors. They are trying to build something that fundamentally endures.
Right. And for you listening, whether you're a seasoned developer who spends 8 hours a day deep in JavaScript, or you're just someone who gets incredibly frustrated when an app dies on your daily commute, this deep dive is going to reveal the hidden architecture that keeps your digital world running.
We're really pulling back the curtain on how the internet actually functions when it breaks.
Which brings us to the tragedy of Timothy, our junior engineer in this story. He starts out completely defeated.
Poor guy.
Yeah. He has built this application dashboard, and on paper, it's a masterpiece. It's completely optimized. He's got these flawless, silky smooth 60 frames per second animations.
And he achieved that by protecting what we call the main thread.
Okay, break that down for us.
Sure. So a web browser generally operates on a single lane of traffic. That single lane has to handle drawing the screen, registering your mouse clicks, running the underlying logic, all of it.
Wow, just one lane for everything.
Exactly. So if you dump massive amounts of heavy data parsing into that single lane, the whole application just freezes up while it does the math. The user clicks a button and nothing happens.
So to avoid that traffic jam, Timothy did everything by the book. He moved all that heavy data lifting over to something called a web worker.
Right, which is essentially a side road, or like a background process where the browser can crunch numbers without stopping the visual animations on the main screen.
He built the perfect engine, basically.
Yeah.
The threading architecture is spotless.
The application itself is running with absolute efficiency.
But then comes the inciting incident of our story. All of that perfect optimization, all that Victorian craftsmanship, it just becomes completely meaningless.
Because of the real world.
Exactly. The client CEO took his laptop onto a subway, lost his Wi-Fi connection for exactly 2 minutes, and was greeted by that pixelated Chrome dinosaur. The app just vanished.
A total failure.
Okay, let's unpack this because it feels so wildly disproportionate. It's like building a multi-million-dollar invincible sports car that completely self-destructs into a pile of scrap metal the moment it hits a single pothole.
That's a great way to look at it.
Why does flawless client-side code completely fall apart just because of a temporary 2-minute network drop?
What's fascinating here is how the senior engineer, Margaret, diagnoses the failure for him. She gives him this incredibly illuminating analogy in the text.
The restaurant analogy, right?
Yes. She tells him, you built a world-class restaurant with a lightning-fast kitchen. In this analogy, the kitchen is using that web worker he set up as a sous chef.
Okay, so the sous chef handles all the heavy computation in the background.
Exactly. It's incredibly efficient. The steaks are perfectly cooked. The salads are crisp. The internal operations are flawless.
But the network connection, the Wi-Fi, is the delivery truck bringing the supplies to the restaurant.
Right. And Margaret points out the fatal flaw in his design. The moment the delivery trucks hit traffic, meaning the moment the network drops, he has designed his restaurant to immediately kick all the dining customers out into the street.
Just, sorry, the truck is late, everyone drop your forks and get out. I mean, that is a terrible user experience.
It really is. The client-side code itself isn't broken. The browser still perfectly knows how to render the HTML. It knows how to execute the JavaScript logic. It knows how to paint the CSS colors.
The sports car still has a perfectly functioning engine.
Exactly. But because the web browser's historical hardwired default behavior is to simply throw its hands up and kill the entire page if it can't reach the remote network, all that perfect local code is just ripped away from the user.
So if the application fails at the exact point of the network connection, then logically the solution must live exactly there.
Precisely. The problem isn't in the kitchen. The problem is at the front door.
You have this beautiful restaurant, but you have absolutely no one managing the front door when things go wrong. And that is where the architecture of the modern web fundamentally shifted.
Which brings us to Margaret's brilliant fix. She tells Timothy they're going to hire a maitre d'.
A digital maitre d'.
Right. And this maitre d' is going to handle network interception. In JavaScript terms, this is the sibling to the web worker he already used. It's known as the service worker.
The service worker. The text details that this is a script that runs completely independently of the web page itself, right?
Yes, completely separate. It doesn't touch the visual elements. It doesn't interact with the buttons or the text. It acts entirely as a programmable network proxy.
Margaret actually draws a diagram for Timothy in the story. She shows the browser on one side, the remote network on the other, and this distinct new layer, the service worker, sitting right smack in the middle.
The maitre d' standing at the podium, right between the dining room and the outside world.
And once you install this service worker, its power over the application is absolute. Every single network request your application makes within that worker's scope flows through it first.
Every single one. It doesn't matter if it's a request for a massive hero image, a tiny CSS style sheet, live API data, or even the foundational HTML file itself.
The service worker intercepts all of it. But wait, I'm trying to picture this mechanically. If I'm routing every single pixel, every image, every single line of text through a separate script before it even reaches the live network, aren't I just creating a massive bottleneck?
It sounds like it, doesn't it?
Yeah, it feels like putting a middleman in charge of every single request would just naturally slow the whole application down.
You would definitely assume that introducing a middleman creates latency, but the architecture bypasses that problem because of where the service worker physically lives.
Where is it?
It isn't a server sitting in another country. It is installed locally, directly inside the user's browser on their specific device. It executes in milliseconds. Yeah. The service worker isn't intercepting traffic to act as a toll booth slowing things down. It's intercepting to act as a protective shield for the user.
So it's essentially acting as a hyperlocal traffic cop.
Exactly. When the internet connection is strong, the service worker just waves the traffic through. It says, go ahead to the network, grab the files.
But when the internet goes down,
that's when the maitre d' earns its paycheck. It catches the failed request from the browser before the browser can panic and trigger the offline dinosaur.
it intercepts the panic.
Right. Instead of failing, the service worker turns around, digs into its own local memory, and serves the customer a cached version of the menu.
So the browser asks the network for a file, the network fails, but the service worker steps in and says, don't worry, I have a saved copy of that exact file right here.
Yes, and the browser happily accepts it, completely unaware that the internet is down. The web page stays alive.
The user doesn't even know the delivery truck crashed. The illusion of continuity is perfectly maintained.
It's quite elegant.
Having the concept of a maitre d' in your head is great. It makes intuitive sense. But it is very different from actually handing them the keys to your network.
Very different.
You're effectively putting a programmable middleman in charge of your user's data flow. How do you actually program that middleman so it doesn't just break the site in a completely new, unpredictable way? Let's get under the hood of what Timothy actually had to build.
The implementation the author outlines is remarkably clean. Timothy has to split his code.
Okay, how so?
First, he registers the new worker in his main application file. He is essentially telling the browser, I am hiring this proxy, please install it. Then he builds the actual brain, the logic for the proxy in a completely separate dedicated file called su.js.
And in that su.js file, the text outlines that he sets up 3 critical event listeners. These are like the 3 phases of the service worker's life.
Plus, the life cycle is key.
First is the install event. This is where he caches the core assets. He grabs the HTML, the CSS, maybe the company logo, and saves them locally.
And he does this using the cache API, which, and this is important, isn't just your standard unpredictable browser history cache. It is a dedicated developer-controlled storage vault.
Second is the activate event, which handles cleaning up old caches. Because, I mean, you don't want to store 5 different versions of a massive website from the last 3 years and completely eat up the user's hard drive.
Oh, definitely not. That cleanup phase is critical. Developers use versioning, like naming a cache V1 and then updating it to V2.
So it looks for the old ones.
Exactly. During the activation phase, the script looks for any cache that isn't V2 and sweeps it away. Good housekeeping is mandatory when you are storing files permanently on a user's local machine.
Makes sense. And third is the fetch event. This is a really crucial one. This is the event listener that actually intercepts the live network traffic.
The heavy lifter.
Right. Margaret points out the raw power of a specific block of code here called event.respondWith. I love the language the author uses. Margaret tells Timothy he has completely hijacked the browser's default network behavior.
Hijacked is definitely the right word.
Normally, the browser attempts an HTTP request to a server, but event.respondWith stops that process dead in its tracks and says, no, I will provide the HTTP response myself.
You are overriding the fundamental hardwiring of the web browser.
Here's where it gets really interesting, because Margaret explains that by checking the local cache first and only falling back to the live network if the cache is empty, Timothy has implemented what she calls a cache-first strategy.
Yes, cache first.
But this immediately raises a red flag for me. If we are using a cache-first strategy where the browser checks the local storage before it even bothers looking at the live internet, aren't we risking serving the user completely outdated information?
It's a very valid concern.
Like if a user visits a new site on Monday and the service worker caches it, and then we publish massive breaking news on Tuesday, won't they just see Monday's version forever? Because the maitre d' intercepts the request and says, hey, I already have this saved. No need to check the live network.
This raises an important question, and it's the central tension of caching any data. You're absolutely right to be concerned about permanently trapping a user in a bubble of stale information.
So how do they solve it?
Well, what the text explicitly clarifies is that cache first is just one tool in the toolbox. The maitre d' is fully programmable. Margaret outlines several other strategies specifically designed to address this exact issue because every file type requires a different approach.
Oh, I see. So how do you handle dynamic data then?
If you are dealing with real-time critical data, let's say an API endpoint that delivers livestock market prices or breaking news alerts, you would never use cache first.
That makes sense.
For that, you would program a network-first strategy. The service worker intercepts the request, immediately tries to reach the live network, and only if the network is dead, only if the subway goes into the tunnel does it fall back to displaying the last known cached price.
That is brilliant. You prioritize the live data, but you keep a safety net.
Exactly. Then there is a brilliant strategy called stale while revalidate.
Stale while revalidate. That's a mouthful.
It is, but it's so clever. This is often used for things like user avatars or articles that update occasionally. When the browser asks for the file, the service worker instantly serves the older cached version so the screen loads in 1 millisecond.
Okay, so it feels instant to the user.
Right, but silently, in the background, it goes to the network, fetches the newest version, and updates the cache for the next time the user visits. It gives you the speed of the cache with the freshness of the network.
Wow. So you are completely orchestrating the flow of information. You use cache first for the skeleton of the app, the HTML layout, the CSS, things that barely change.
Yep.
You use network first for the actual live data pumping through its veins. And you use stale while revalidate for the assets in between.
You are building a custom, highly resilient routing system directly inside the user's device.
But because this capability to hijack network traffic is so profound, web browsers are incredibly paranoid about security, aren't they?
Extremely paranoid, and for good reason.
They require strict ground rules before they actually let you wield this kind of power. Margaret outlines 2 golden rules for service workers before Timothy is allowed to test his code.
What's the first one?
The first is non-negotiable. Service workers can only run over secure HTTPS connections. Which, I mean, makes total sense when you think about the mechanics.
It really does.
If you have a script that can intercept every single network request, read the data, and rewrite the responses in the wrong hands, that is the ultimate nightmare scenario.
Oh, absolutely. If you are sitting in a coffee shop on an unencrypted public Wi-Fi network and a malicious actor manages to inject a fake service worker into your browser, it's game over.
They could see everything.
They could seamlessly intercept your banking requests, steal your passwords, or alter the data you see on screen, and you would never know because the proxy sits below the level of the visual web page.
That's terrifying.
Which is why the browser mandates HTTPS, to cryptographically ensure that the script you are installing is authentically from the website you actually intend to visit.
It is the ultimate background check for the maitre d'.
Exactly.
And the second golden rule Margaret brings up is about the service worker's life cycle. The text notes this is where a lot of developers get incredibly frustrated and tripped up.
Oh, it causes so many headaches.
She explains that when you push an update to your su.js file, the newly updated worker won't fully take control, meaning it won't start intercepting those top-level navigation requests like refreshing a page until all existing tabs of the application are completely closed by the user.
Right. Unless the developer explicitly codes a complex workaround to force it to skip waiting, the browser enforces this waiting period strictly.
So what does this all mean? Let me try an analogy here to visualize why the browser is so stubborn about this.
Go for it.
It's essentially like changing the locks on a massive commercial building. You can bring in the locksmith, you can cut all the new keys, you can prep the new deadbolts in the hallway.
Okay.
But the building manager will not allow you to actually swap the physical locks on the doors until every single employee has clocked out, left the building, and gone home for the night.
That perfectly illustrates the concept of state consistency.
Because if you swap the locks while people are still inside moving between rooms, they might get trapped. Or an employee's old key suddenly won't open a door. They need to do their job. You'd have absolute chaos inside the building.
That is exactly the rationale the browser uses. Imagine a user has 3 different tabs open to your web application.
Right.
Tab 1 triggers an update to the service worker, and the new worker immediately deletes an old cached image to make room for a new layout. But tab 2, which is still running the old code, suddenly tries to load that deleted image.
Oh, I see. The application would completely crash.
Exactly. The browser prevents this chaos by waiting for a clean slate. Everyone clocks out, meaning all tabs are closed, and then the new maitre d' safely takes over the podium for the next shift.
It enforces consistency so the app doesn't break itself. Okay, so Timothy has built his separate su.js file. He's set up his intelligent caching strategies. He understands the golden rules of HTTPS security and the tab lifecycle.
He's ready.
We finally arrive at the climax of our story in the Victorian library. Timothy saves his files, refreshes his dashboard to install the worker, and then he initiates the ultimate test.
The moment of truth.
He opens up his Chrome developer tools, navigates to the network tab, and deliberately toggles his connection to offline. He is intentionally forcing the delivery trucks to crash into a brick wall.
He is simulating the exact subway scenario that previously caused total catastrophic failure.
He holds his breath and clicks refresh on the browser. And the author gives us this incredibly satisfying resolution. The dinosaur does not appear.
Success.
The dashboard loads instantly. The underlying HTML structure is perfectly there. The CSS grid is completely intact. The JavaScript framework renders flawlessly.
Now, the text does note that the actual data grid on the screen is empty, right?
Yes, because obviously it is pending a live connection to get the latest numbers from the server. But the application itself hasn't crashed. It is alive, responsive, and patiently waiting.
Which is such a profound architectural shift from where he started the day. His complex threading architecture is finally complete.
The web worker handles the heavy mathematical lifting so the screen never freezes.
And the service worker handles the network interception so the app never dies.
And Margaret leaves him and the reader with one final crucial note. She explains that this specific combination of technologies is the absolute foundation of progressive web apps, or PWAs.
Progressive web apps. This is where all of this abstract technical plumbing finally impacts the everyday user.
If we connect this to the bigger picture, a progressive web app is essentially a standard website that has been so thoroughly engineered with these service workers and caching strategies that it transcends being a mere web page.
It behaves almost exactly like a native compiled application you would download from a dedicated app store.
Because it can load instantly offline, it can be installed directly onto your phone's home screen. It can send you push notifications.
Exactly. Because it has that programmable proxy managing the front door and a local cache of all its necessary files, it doesn't need a constant, fragile umbilical cord to a remote server just to exist on your screen. It is self-sufficient.
So, to pull all of this together, we've explored how modern web applications have evolved from these incredibly fragile constructs that shatter at the first sign of a dropped signal into incredibly robust, resilient systems.
It's a massive leap forward.
By separating the heavy computation to a background web worker, our sous chef, and handing all the network traffic to a service worker proxy, our matrix developers can craft an experience that survives the worst subway commutes and the spottiest airplane Wi-Fi.
They've engineered a way to gracefully handle the messy reality of network failure, transforming a catastrophic crash into a minor, invisible hiccup.
For you listening, the next time you are on a long flight or deep underground on a train, and you tap on a web-based article or an application, and it miraculously continues to function, load, and let you read without any Wi-Fi whatsoever, know that you aren't experiencing magic.
Not magic at all, just really good architecture.
You are witnessing a digital maitre d' working incredibly hard behind the scenes, intercepting your requests and serving you directly from the cache to protect you from the offline dinosaur.
It's a beautifully elegant, invisible solution to a problem we all used to think was unsolvable.
It really is. And it leaves us with something quite provocative to think about as we wrap up. If a service worker can intelligently cache an entire application to run seamlessly without an internet connection, if a progressive web app can perfectly mimic the behavior, the speed, and the offline resilience of an installed native application, how much longer will the traditional App Store model even exist?
That is the million-dollar question.
Why force users to jump through hoops to download massive gigabyte-heavy files from a walled garden controlled by tech giants when eventually everything might just be a beautifully crafted URL that instantly installs itself the very first moment you visit it?
It really makes you wonder if those perfect, state-of-the-art skyscrapers we talked about at the beginning are finally ready to stand entirely on their own.
Definitely something to mull over next time you're offline.
Yeah.
Until next time, keep diving deep.